Hi, everyone. Again, as I pointed out before, the intention is to convert these PowerPoints, these presentations that were made to students in the JMED Math Clinic. And it's been a lot of fun just converting these because they were done live, but afterwards students keep coming and saying, hey, can you have this video? Can I have this video? Or is there a video recording of it? So the idea is that we'll put these together and I'll go through constantly just trying to find lessons that I've done and just made them into videos for students in the math clinic. So today's lesson is one that's done before, but the videos will be great. Knowing how to find the volume of of 3D shapes in reality, so prisms, pyramids, and spheres. And I'll just go through the basics. These are not advanced stuff. It's just to get you the absolute basic in terms of how you do it. And then after that, you can then see other examples that I can get to. And remember that you can always reach out to us to join this clinic by sending an email to jmedetf@gmail.com. It's maybe right here. Yeah, right here. So you can always be able to do that. So without further ado, I'll get the lesson going. So the objectives for today's lesson is to know how to find volume of prisms and pyramids. And perhaps we may not get into unfathomable problems, but it's something to think about. So we have prisms. Prisms are pretty much the most common type of solid that's out there, you know. And if you go back into your learning about solids, you know that solids have different parts. So for example, you'll talk about the faces. Now, I describe the faces are the parts that you can put your hand on. You can rub that. That's maybe something you'd have done in grade 6, maybe, or grade 7, or even earlier. But it's the smooth part, you know. So anywhere that's flat or you can rub your hand over it smoothly, that's going to be a face. And then we talk about edges. Now, by definition, an edge is anywhere two faces meet. So, for example, this base face, this frontal face here, and the top, wherever they meet, you get an edge. And the last part of a solid that you need to know as well is where the edges meet. So where you have 3 or more edges meeting, you get what we call a vertex. Now that's just to bring you up to speed with the stuff that you've been familiar with. So I'm not sharing that as new knowledge, but if it's something new for you, then you can check out those words: faces, edges, and vertices. And there's a formula that connects them. It's called Euler's formula. You can check that out as well. So when we look at a prism, what makes it a prism is really a basic idea that there's a constant cross-section. And essentially, if you slice it, imagine it to be like a loaf of bread. If you slice it, as you go through, the shape that's at the front is the same throughout. So the shape doesn't change. So for example, the cross-section, if we go from front to back, will be looking like this rectangle. And that's a constant shape all the way through the solid. So the idea is that it's a prism, if that is obvious. Yeah, obvious there. And in most exam questions, they'll say it's a prism. But if it is a prism, you can tell by looking at it and looking at the cross-sectional shape. And in this case, this is a cuboid, and there are many cross-sectional pieces to it. You can go from the side. So that depends on the orientation in which the problem is presented. But the idea is that normally when you get a question, it will identify these. And for cuboids, you'll have a lot, but for other shapes, the other solids, the cross-section is quite clear what it is. So we'll have a look at a few of those. All right, so the basic thing to bear in mind is that the volume of the prism is equal to the cross-sectional area multiplied by the height. Now, height is quite an arbitrary term, and I'll explain what I mean. Because when we identify the cross-sectional area and multiply by any other dimension that would be present. So it could be a height. So for example, if we're talking about like a tower, then the height is going to be the distance measured upwards. But if you're talking about like a swimming pool, then that height can now become a depth. It's just the other measurement that you're using to determine how big is the volume of that that space. And the cross-sectional area, once identified, the height or depth or thickness, anything like that, would be like the perpendicular distance, like going in the opposite direction from it, which helps you to be able to do this. So cross-sectional area times height. For a cuboid, the volume is simple length times width times height. And the reason is because if the area, the cross-sectional area, happens to be a rectangle, then length times width would be the area of that, and then height would be followed up as part of the general formula. Now, if we look at another type of prism, why is it a prism? There's a constant cross-section going from one end to the other, and that's the triangle that we can see at the front and at the back. That makes it a prism just by virtue of that. In this case, we'd call this a triangular prism or triangular based prism, whichever way you want to go, but triangular prism is okay. The prism is normally named by the shape that is in the cross section. So if they say it's a hexagonal prism, then it means that the cross-sectional piece, the cross-sectional shape, is a hexagon. And likewise, if it is a square-based pyramid, now most times once we move outside of certain shapes, the names are very descriptive. But like the one I showed you before, this has a name, it's called a cuboid. But if you call it a rectangular prism, I think you'd be on the right track as well. But it's a cuboid. All right, so, and again, the volume is a cross-sectional area multiplied by the height. The cross-section is this here is a triangle, so it's a half base times height, or whatever formula that works to find the area of the triangle multiplied by the height in this case, or the length, depending on how we consider it. We'll see in an example. So here we have a triangular prism or triangle-based prism. Both are equally okay. So I don't think you lose marks for calling it a triangular-based prism. But we're also finding the volume of the prism, and we look at the important information here. We can see the cross-section. As I said, for triangles, it's quite obvious what the cross-section will be. So it's going to be a triangle, goes all the way through. The height and the base are clearly defined because we can see that right angle sneaking in here, yeah? And then the length or thickness, depending on what it is 18. All the units are the same units, all of them are in the same. Something to check all the time because that could cost you marks if you're not being smart about it. So let's have a go at this. So we know that the volume for prisms is cross-sectional area times length. So all we need to do here is identify the cross-section, which we know is a triangle. We're going to use the formula half base times height, which will give us, and times the length of this shape, okay? Substitute the values. Standard procedure, we just replace what we know. We know the base is 12, the height is 9, the length of the shape is 18. Substitute, and then from here, it's really just calculating and getting to the answer. So the final answer is 972 cubic units. And with area, we put a 2 to represent squares because effectively we're trying to find out how many 1 centimeter cubes can fit into this shape totally and completely without leaving any spaces out. And it's going to need 972 centimeter cubes to do this. All right, so when you're doing volumes, that's kind of like what we were thinking. How many cubes can we pack inside? So that's example, one of the examples. Let's look at another example. Here we have a cuboid. As I said, sometimes in an exam, they'll tell you what it is. That way you know some things are true. For example, if they say it's a cuboid, you know that this must be a rectangle. And so if you're doing additional work, you don't need to know that the corners are right angles because it's a cuboid and that conveys certain information. So formula, cross-sectional area times height. Again, we're going to choose a cross-section. Length times width times height, which is more the standard formula. And then we just do 10 times 15 times 20. So in this sense, for a cuboid, just multiply the 3 numbers. Nothing to worry about. Simple multiplication. And that means 3,001 centimeter cubes would fit inside. And you can do simple checks to know if that's true. Quite straightforward, because if we even fit 10 across here and 15 across here, in the first layer, we'll get 150 centimeter cubes. Just in the first layer. 10 across, 15 across. Make sense? And then because it's 20 high, then 20 times 150. So we'll end up with 3,001 centimeter cubes fit neatly into the shape with no space missing. Effectively, when you're doing volume, that's what you're checking. How many centimeter cubes or millimeter cubes will fit into the shape. Let's have a look at the volume of a cylinder. Now, a cylinder is a prism, but it's maybe what we'd call a circular prism or circular-based prism. It's a special name. It's called a cylinder. And certain information are important here. The cross-sectional area, in this case, the cross-section is a circle. So our approach to it is to find the area of the circle. Now, importantly, in a circle, we have pi, which you maybe will see in one of the videos. We have radius squared times height. Now, notice in this diagram, we're seeing the diameter. How do we know? It goes all the way across and it went through the center. That dot represents the center of the circle. So we know it's a diameter. We also know the relationship between the diameter and the radius, because the radius is really the distance from the center to that. So if the diameter is 14, it means the radius is 7. So we substitute those values, pi r squared, and then we multiply by the height. And simply, we do the calculation, we round it to the desired level of accuracy, and we have our volume. Now, in this case, we have like 0.58 centimeters, but that's the level of accuracy that will come out. That will fit 1,539 and roughly a half inside of it. Okay? A sphere, another circular kind of three-dimensional figure. It's a sphere. A sphere has a special formula. It gives information here. A sphere is just anything like a ball. Yeah. It has one face, no edges, no vertex. Because if it has one face, remember that faces meet to create edges and edges meet to create vertex. So if it only has one face, then yeah, you don't know. So if the diameter is 10, then the radius is 5. Always remember these relationships, you know. The diameter is a longer word than radius. So if you're not sure, then you could always go diameter is a longer word. So diameter is one long word. Radius is a 5 cm. Okay? So sometimes you go, I don't know the difference. Well, you know the relationship. What you might not remember is which one's bigger. So diameter is a longer word than radius. That will help you, certainly. So volume equal cross-sectional area times height. We know the formula for volume of a, so ignore that first slide, sorry. The volume of a volume, this is not a prism, so sorry about that. So the volume of a sphere is just 4/3 pi r cube, okay? 4/3 pi r cube. And that's just the formula for it. So that's done by using differentiation and all that to figure out what's the volume. So we continue by substituting what we know, and we end up with 523.6 centimeter cube. And that's how you find the volume of a sphere. It's quite straightforward once we know the radius. Just one input is required. All right. Here we have a pyramid. Now, a pyramid is a special shape that we need to be familiar with as well. The formula for pyramids, again, is a general formula. So I don't need to do every type of shape. You just need to understand that for a pyramid, unlike the prism, there's going to be 1/3, but everything else is the same, just 1/3. And you may be able to see why, because it recedes. You know, it starts to converge at the top, and by the time it gets to the top, you've lost 2/3 of the prism itself, and it becomes a pyramid. So the volume of the square-based pyramid with a height of 27 cm and the length of base is 9 cm. Since base is a square, the length and width are the same. That's just my thinking, you know. I tend to think about what's going to be useful here. So 1/3 base area times height, and that height has to be the perpendicular height. So from the center, from the lowest, from one point to the top. All right, doesn't matter what the shape of the prism is, the pyramid is as long as you can get that vertical height, you're good. Find the base, multiply by the vertical height, you'll be okay. Substitute those volumes. Because it's a square, we're going to use length squared times height. Substitute 9 times 9. Yep, because it's a square, so 9 times 9 is 81, and then we know that the height is 27. Just do the math, and we end up with 729 cm cubed. At all times, if you're working through any of the problems, just pause them if you want to do them yourself, and then you can get the chance to practice that, all right? So that's how we find the volume of a set of pyramids, squares, cylinders, and just try and understand how you find the volume. Remember, volume is really measuring capacity, how much something can hold. Maybe later on I'll work with some more deeper questions, but for now I'm just going through basic examples to give you that background so you can apply that in simple questions first. Because with math, when you can do the simple stuff, then you'll be able to apply it to unfamiliar situations. So thank you again for listening to that one. As I said before, this is just part of the math clinic. Some simple examples for people who are working through the syllabus. If you need any help, just let me know. I'll work you through those. But these are just step-by-step examples of how to find volumes of prism, pyramids, and spheres. And again, if you know the formula, if you understand the basic formula, you'll be in a good space, because it means that you can apply it to different situations. So try not to just learn 10 different formulas. Just understand that for prisms, cross-sectional area times the height. For pyramids, it's 1/3 cross-sectional, 1/3 base area. If you think of it as a cross-sectional, it will help as well. 1/3 base area times height. And then for spheres, it's just one formula. So you can maybe think about that one, all right? All right, thank you very much. Again, another video done. And hopefully, you know, that will help you to continue to develop in your mathematics. Feel free to ask questions. And as usual, you know, we're always here. So the email that you can reach out to us, jmedetf@gmail.com. The classes are free. They run every Sunday at 11 a.m. Eastern time. Sign in. Anyone's welcome. First come, first serve. And what we try to do after each session, we provide a video. So if you missed the session, you can still see the video of the session, but you must register. So if you email, you'll get the first step in the registration process. All right. Thank you, and hope that was useful for you. Just another video from the Math Clinic.